Okay, so we've seen how we're going to go about our analysis. We're going to be using log transformations. We're going to be trying to make data look approximately linear on either a log scale or a log y scale or a log x scale, and then we're going to conduct some analysis. So now we want to get to the point of how do we fit these lines. So we know that fitting these lines, what is it called? It's called regression analysis. So this is our current topic, talking about regression models. If we don't have linear data, what we're going to start off with is using some transformations. Now, obviously, we can build up complexity. We can have quadratic terms, and we can have all sorts of curvy shapes. We're just starting with the first steps of learning the tools of analysis. We want to conduct some transformations. So there are some formal ways of looking at this, or there are some intuitive ways of trying to work out when things look linear. We're going to just look at different scatter plots. So we're not going to be into formal testing. We're going to be using visual analysis of the data. So that means you have to think. It means that you can't mechanically press a button and say, oh, I choose this one. You're going to have to use judgment. You're going to have to look at the data, right? So this is learning one of the most critical skills of analysis. You need to start by looking at the data carefully. So that's the skill that we're building up. Now we want to get an estimate of the intercept of a slope. Okay, so I would say that some people would argue that you can collapse all of these frameworks into one, but in classical statistical methods, which is the kind that we're covering here, there are other kinds. There are Bayesian methods. There are some other things that you can talk about, but generally there are three approaches that can be used. The one that's most commonly used, especially for the data that we look at, is called least squares, and particular ordinary least squares, or OLS. So that's the one that we're going to be learning about. Now, how do we motivate this, or how does this decision rule work? Okay, so we fit our line to the data, and remember, it's not an exact fit. It's just describing how things work on average. So we have these errors, and we're going to find the line that minimizes the sum of the squared error terms. So this is very similar language to the language that we would use for ANOVA. Sum of squares, okay? We're squaring things. Why are we squaring things? Because positives and negatives cancel out. So let's just have a quick look at how this might work. Okay, so here I've got, I'm trying to model the way that wingspan grows in birds as they age. So here's my data. I've just the first three observations in a data set, and you can see that the trend line is sort of lying between them. It's not a perfect fit to the data. So in my formal notation, I have my first point here, which is x1, y1, okay? So it's the first data point in my data sample. So I've used that subscript 1. So we've been familiar with using subscripts, i's and j's. Now, we have the vertical distance. So I'm saying that the error 1, is the difference between my trend line and the actual data point. Okay, so I'm going to denote that E1. The second observation in my data set is x2, y2, and I've got an error for that too, which is E2. And then we have E3. So the thing that we're using our decision rule for is to fit a trend line to the data, such that we minimize the sum of the squared vertical distances, okay? Why are we squaring them? Same reason that we've done that for the ANOVA stuff, because the positives and negatives cancel out. So formally, the regression or the trend line, so it's a regression trend line, so the type of analysis we're doing is regression analysis, it minimizes the sum of the error terms, okay? And the notation that we can use for all observations is EI squared, okay? The sum of the squared error terms. So what are we doing? I have some data here. I have some wingspan growth data. I could, put all sorts of lines in here. I want to put, why do I pick this line over my other possible lines that I could have fitted to the data? I pick this because I use this decision rule, which is to minimize the squared error terms, and this is a good decision rule, okay? From that decision rule, I get an estimate of the intercept and an estimate of the slope, or an estimate of alpha and beta. Okay, so in this specific case, we have wingspan is equal to the intercept plus 0.27 times age, where age is measured in days here. So it's saying that wingspan increases by 0.27 centimeters on average for each day. All right, so what are our future steps? So we've really covered the theory of the analysis in this lecture. What are our future steps? Similar to the way that we've looked at our other tests, we're going to look at loading data into R, which we're very good at now. We're now going to look at some transformations of data. So it's just the same transformation that you've seen repeatedly, which is the log transformation. We are not going to be using box plots but scatter plots. So we're going to have a slight different notation for our plots, different features to play around with. We're going to be estimating a trend line. So we're going to introduce a new function, which is LM. So that's an easy one. That's just the function that we're going to use. LM stands for linear model. And the way that we're going to estimate these models is just the dependent variable tilde. So the squiggly line is tilde, explanatory variable. And then, just like all of our other analysis, we want to say something useful. So we're going to have some interpretation. And the things that we're going to be focused on for our interpretation is the slope of the line. What does the slope mean? So that means it's going to be really important for us to know those log different terms. Okay, and that is an opportune time for a break. And fortunately for you, it's time for Marit to cover some materials. So enjoy the material from Marit. Bye-bye.